The objectives of today's lab are to observe the motion of a falling projectile, then to use Tracker to track the object's motion, and use GlowScript to create two computer models, one that takes drag into account and one that doesn't, and then in the end compare the observations to the two computer models. The purpose of this lab is to perform an experiment that will show a practical application of Newton's second law. We'll be using the momentum principle, which says net force equals the change in momentum over the change in time, to analyze an object falling at terminal velocity. For this lab, we'll be observing a block of foam that weighs about 45 grams. Here's a video of this foam block falling. Now we will use the Tracker application to track the motion of the falling foam block. As you can see, there are purple lines that mark the axes along which the foam block will fall, and then there is a ruler for scale that measures about 0.305 meters. As the block falls, the center of mass is marked frame by frame to create the position versus time graph on the right. Here you will see it plotted as the block falls. Some key takeaways from the Tracker application are that position versus time graph starts off curved then straightens out. We know that when it's curved, it's accelerating, and when the slope is straight, that means there's a constant velocity. So that means that in the end, the block is falling at a constant velocity, or is falling at its terminal velocity because the force of drag is equal to the force of gravity, causing it to not accelerate any longer. Now we'll use GlowScript to create two computer models. We're given a starter code which we can modify using our knowledge of Newton's second law, or the momentum principle, to modify the variables as needed. In the end, we'll be creating two computer models, one that models the fall of a projectile object without considering the force of drag, and one that does consider the force of drag. Here's the code we'll be modifying for the computer model that shows the fall of the projectile object without the force of drag being taken into account. For this one, the net force vector is simply just mass times gravity in the negative y direction, no drag taken into account for this model. And to update the velocity of the ball by each frame, we use the velocity update formula derived from Newton's second law, which takes the original velocity plus net force divided by the ball's mass times the change in time, and then we apply this new velocity to change the ball's position, which is the original position plus the average velocity of the ball times the change in time, and the change of time is simply one frame of our video, which is 1/30th of a second. To create the model that does take drag into account, we need to add drag to the force of gravity in the net force vector. To do this, we have drag proportional to the velocity of the ball squared, and then we multiply it by a proportionality constant that gives us results similar to those observed in the Tracker model. Now here you can see the results from the computer model that does not take drag into account. On the position versus time graph, it's a steady curve the entire time, and you can see on the velocity versus time graph, it's a constant slope, meaning the acceleration is constant, the acceleration being acceleration due to gravity. As you can see here, the model that does take drag into account yields a different result. At first, the position versus time graph, you do see a curve, but then it turns out to be a constant slope after that. And if you look over to the velocity versus time graph, it starts off at a slope and then it flattens out. This is because it eventually reaches terminal velocity where the drag is equal to the force of gravity, leading to have a constant velocity. Now if you compare the results here, you'll see that the model without drag obviously falls a lot further because it's accelerating the whole time rather than traveling at a constant velocity at the end due to it reaching terminal velocity. Whereas the observed Tracker data and the model that does take drag into account, you'll see they flatten out and end up traveling at a constant velocity and do fall a lesser distance. And there's a slight difference between the Tracker model and the model that does take drag into account on GlowScript, but it's a small amount and probably comes down just to measurement error with Tracker. For which model shows terminal velocity, you'll see that the model that does not take drag into account is on the left, and it has a constant acceleration and does not converge on any single velocity, whereas the model on the right, where drag is taken into account, it converges on a velocity at the end, which means that this ending velocity is a terminal velocity. For the question, if a foam block is thrown down with an initial velocity, will it still end up on the same terminal velocity? The model on the left shows that from rest, the terminal velocity converges at about -2.4 meters per second, And the model on the right shows that if the foam block is given an initial velocity of -5 meters per second, simulating it being thrown downward, it will still converge on the same -2.4 meters per second in the end.